very much. I want to start by thanking the organizers for inviting me to come to Warsaw. It's the first time in Poland, so it's very interesting for me. In addition to all the academic stuff, that's of course also quite interesting. So what I will do, it's very loud, is it not? Can you turn it down, or should I just? Okay. Okay. Yeah. So I will change focus a little bit as compared to the previous talks. So what I will do is I will focus on many body properties of ions in Bose-Einstein condensates or Fermi gases. So I will assume in this talk that you have achieved quantum degeneracy. And what I will do is I will introduce a simplified model for the atom-ion interaction, which you can then comment on. I hope this is a workshop, so I look forward to hearing input on that, how realistic this many-body model is, or this microscopic model. So I will do this in the beginning. I will tell you what I focus on, which is quasiparticles and their interactions. So I'll try to motivate, right, this is important. Then I will discuss the atom-ion interaction, which is dangerous in this audience because you know much more about it than I do, but I will tell you the pseudopotential that we put into our many-body theory. And then I will tell you about basically what comes out of this many-body theory, which are these quasiparticles, charged molecules or polarons, and also the interactions between them, which is often neglected in this field. Good. So somehow it doesn't react. That's fine. So why there has been the big fuss about quasiparticles and polarons in atomic gases, and this is because this is just a motivational slide. It's because it's quite an important concept. So it comes about from the fact that normally if you have a many-body system, you can formally write down the Schrödinger equation, but that's basically very difficult to solve unless there are no interactions. If there are no interactions, you just get an ideal gas. We can solve this in textbook quantum mechanics, and in the classical regime, it obeys the ideal gas law. The problem is when the particles interact, it's just intractable. And there's a whole industry of physicists trying to solve this problem with interactions. And one of the very, very powerful tools is Landau theory of quasiparticles. So his idea was that if you take a non-interacting system and you adiabatically increase the interactions between the particles to get to the system you really want to understand, if there are no phase transitions on the way of this adiabatic increase of the interactions, there should be a one-to-one correspondence between the particle excitations over here, which are simple to describe, and the low energy excitations over here. So the low energy excitations become particle-like. They are not exactly like a particle, like in this case, in this cartoon. They are not like the bare horse or bare particle. They become dressed by interacting with the surrounding medium. So they become what's called a quasiparticle. Their energy changes slightly, or maybe a lot, and their mass changes. But if you have this quasiparticle description, then you basically end up with describing this interacting many-body system in terms of quasiparticles that interact typically quite weakly. And that makes the description much, much easier, and it's used across everywhere in physics. So across energy scales that differ by a factor of 22, 10 to the 22, all over they use this idea. So it's a very powerful idea, and it has been this adiabatic increase of the interaction between the particles was a Gedanken experiment by Landau. He said, let me just do it. Of course, he couldn't do it in nuclei or electrons and crystals and so on. But since 2009, it's already now, 13 years, it has now been done, this Gedanken experiment has been done in neutral gases, where they use this Feshbach resonance to take a non-interacting, an impurity inside an atomic gas, and then they just adiabatically increase the interaction between the impurity atom and the surrounding medium by using a Feshbach resonance. And this has then generated a lot of papers and a lot of activity, because it's nice. You can then really study quasiparticle properties microscopically, and there's a bunch of theory papers and many, many beautiful experiments, both for putting impurities inside Fermi gases and also Bose-Einstein condensates. But all these have been for short-range interaction. So the atom-atom interaction between neutral atoms is short range. It's 1 over r to the 6, and for all intents and purposes, you can just describe it by one length scale, which is the scattering length. So we have been in Aarhus, as you will also hear in the next talk, we have been very active in this field. But now there's this new, seen from the many-body side, new bunch of experiments coming up, and this is just a subset of them, not representative, but there seems to be, and also from I hear from these talks at this conference, there seems to be significant progress towards creating quantum degenerate systems where you have an ion instead of a neutral particle inside a quantum degenerate gas. So that made us turn our attention to this problem. This is a theory talk, by the way, so it's not experimental. So we will now, I will try to convince you or tell you what type of physics you can see if you reach the quantum degenerate regime of putting an ion into a quantum degenerate Bose gas or Fermi gas. So this is again, so now we come to the atom-ion interaction. So you know much more about this than I do, but I'll tell you what we put in to our theory. So it's inevitable fact of the fact that, a consequence of the fact that the ion polarizes the atoms, that the long-range part of the atom-ion interaction goes as 1 over r to the 4th instead of 1 over r to the 6th if it's a neutral system. And it's proportional to the polarizability of the atoms. That you know much better than me. So the atom-ion interaction has this 1 over r to the 4th long-range tail. And it just turns out that the length scale, if you define the length scale, you call this r star, we call it r ion. Anyway, so this has a typical length scale. And this length scale is not short range. It's typically 100 nanometers or so if you put in the atomic masses and the polarizabilities. And that means, and that turns out to be more or less the same distance as that between the atoms in a quantum degenerate Bose-Einstein condensate or Fermi gas. That means that you have no separation of scales at this point. So you need to have, if you want to do a many-body theory, we want to look at as simple potentials as we can, interactions as we can to do our many-body theory. Unfortunately, we cannot use a delta function potential or a short-range hard sphere potential. It's just wrong. So we have to do something else. We have to really include this 1 over r to the 4th tail in the theory. However, and this is, I hope that you agree with me or we can discuss this, when the atoms and the ions come close to each other, they will start, the electron clouds will start overlapping. And so there will be a short-range repulsive core. But this happens at a much shorter length scale. This is not at the order of our ion. There's a separation of scales here that the hard core, where you start getting, it's not hard repulsion, happens at a length scale that's much shorter than this typical length scale here. And this is important because that you have the separation of length scales. Then there's another complication of this potential, and that is, of course, that it has many bound states, as we heard numerous talks here. And what we will assume, so we're motivating building up a pseudopotential to put it into our many-body theory. So we have this separation of scales, that's one thing, between the short-range repulsion and the long-range R ion here, R star. But we also say that we are not so ambitious that we want to include all the bound states of the potential. We assume that it's only the highest energy state that matters. It's only the highest energy bound state that has any role in the physics. So we just neglect this. So with this, we can take, this is not our idea, this has been pushed forward before us. We use a pseudopotential, this effective potential, which has a long 1 over r to the 4th tail. And then it has a short-range repulsion when r becomes smaller than c. And we use a very small c here. We don't use c equal to r ion. It's much smaller. And the idea is then, if this potential recovers the correct energy of the highest bound state plus the atom-ion scattering length, we hope that then this is universal enough that it predicts the correct physics. That means that all these low-energy scales here are unimportant. At this short-range physics here, the physics doesn't depend on this short-range propulsion here as long as it's there. So this is the pseudopotential. And what we will do is, we heard now that there are now beautiful experiments where they actually see Feshbach resonances between atoms and ions. So we will model this by simply just varying b, this parameter b here. So c determines where it becomes repulsive, which we keep small. And then we vary c so that we can go through a bunch of Feshbach resonances where new bound states enter here. This is what we will do in the rest of the talk. So now when we have this pseudopotential here, we can do our many-body theory, we Fourier transform it, and we just now, let's focus first on an ion in a BEC. So here's the Hamiltonian. So let's just see, then you have to do approximations. You have to do something to go forward. And just to motivate the approximations we do, we look at, if you look at the number of atoms around the ion, So just that's the surplus density minus the equilibrium density of the BEC around the ion. If you can do some thermodynamic arguments for how many there are. And if you assume mean field theory all the way through, you get that you should expect, due to the strong atom ion interaction, that there are many atoms, bosons, around the ion. This is different from when you put impurity atoms into a Bose-Einstein condensate. Neutral impurity atoms, you typically have one, maybe two bosons around the ion. Here you can expect many more. So you have to use a different ansatz to try to describe this. And we are now doing a variational calculation. So we say, okay, the wave function describing the ion inside the BEC is basically you put the ion in here, but then you generate a bunch of Bogoliubov modes. So we use Bogoliubov theory for the surrounding cloud. And this takes into account the dressing around the ion, so you can actually calculate how many ions you have inside how many atoms you have inside this dressing cloud. This is an approximation that we took from what has been used in the neutral gases. Okay, so then you crank away and you calculate what comes out. What are the energy what are the eigenstates of the system? And this is plotted here as a function of B. So when we vary B, we vary the scattering length up here. Unfortunately, this talking thing, can I remove that? I can put it somewhere up here. Yeah. So this is A up here, and this is the B and the corresponding A up here. So let's look at what this spits out, and this up here is energy. So when you have bright colors, it means you have an eigenstate, or it's a many-body system, so you typically have a continuum of eigenstates. But here's one here, very sharp feature. It's called the spectral function. Whoops. And I don't know what's going on. Funny. Okay. Okay. So first you see this branch here, and this is this is very well known for us from the neutral gas community. This is an attractive polaron. So this thing here is basically just the ion. It's a mobile ion. It's not trapped, by the way. For all of you with the RF trap, it's more along the experiments of Tillman-Fau that the ion is mobile. I forgot to say that. So you have a quasiparticle excitation here, and as a function of B, when it becomes deeper and deeper the potential, then it starts supporting a bound state here. This energy of this attractive polaron goes down. So just look at the red line here. And the number of particles inside the dressing cloud, we can also calculate that, is indeed at the order of 10, 20, something like this. And it's an attractive polaron. We know this because if we use a well-known workhorse from the neutral gas community, which is called the ladder approximation, it basically recovers the same physics. So this is maybe not, it's just a charge analog of a polaron. Then you have another branch here, which we will say is then another polaron, because here, when you go from here to here, the scattering length is positive, and then it becomes negative here, and you see that the energy of this state here goes through zero. So if you just think about it in mean field picture, it just means that this ion experiences a repulsive force with the atoms around it. Its energy is above zero. It says P equals zero impurity ion, and then it goes through zero down to attractive when the scattering length becomes negative, where there's attraction. And if you look at the number of particles in the dressing cloud, that also is negative up here, so pushes away the atoms. And then when you go towards the attractive side, it actually pulls in the atoms. So that's all consistent. So you have these two quasi-particle branches, repulsive and attractive polaron, kind of like what happens in the neutral gases. What is interesting are these, well, there are some differences, but due to time I won't cover it. There are some differences here. But the qualitative new feature, I would say, are these lines here. What are those? To understand those lines here, these faint lines here, you have to realize that when B is smaller than this value here, you have a bound state. And over here, you actually have two bound states. And then the interpretation of these lines is basically these are molecular states. So this is the ion trapping simply binding one neutral atom and forming a dimer state. And this you can argue by looking at so we threw another theory at it where we looked at the scattering between a polaron and an additional atom, and we looked at where are the poles in the scattering matrix, and those match exactly. Those are the dashed lines. They match exactly these lines here. And then the next line is, we do the same. It's actually the ion catching one more, and so on. And this we can identify by doing this kind of theory here. Of course, it is an approximate theory. So this is what is an ansatz. It's a variational ansatz. And when we throw another, it's a diagrammatic ansatz, we also throw at it, but these are approximate theories, but they yield consistent predictions. Then we have these stars here, and this is where our ansatz where our theory breaks down, because we use Bogoliubov theory. So when the surplus of atoms around the ion becomes too big, you break the diluteness criterion of the BEC, and then it's just not reliable. So these things, then basically, the stressing cloud around the ion becomes too dense for our theory to be able to describe it correctly. So we stop it here. Yes, and then there's a bunch, due to time I will not go through it, but you can argue how the spectral ways of these things behave. I would rather, so then we can go to the Fermi gas. We can also put it into a Fermi gas. It's the same, it's a mobile ion. Again, we put it into a Fermi gas just to tell you what goes on. And here we use a simpler theory, actually, which is just this ladder approximation. And the reason we use that is because we know it has turned out to be super reliable, super accurate, and surprisingly accurate for neutral impurities inside a Fermi gas due to cancellation of high order terms. We don't know whether it's accurate for this atom-ion system because the atom-ion interaction is longer range. So maybe this Fermi cancellation of higher orders will not be as efficient. But since we are the first to do this, we throw our theory at it to see what happens. And you basically get the same kind of physics. You get attractive and repulsive polaron branches, which are charged analogues of what's called the Fermi polaron in the neutral gas community. There's a bunch of differences. They behave differently. So basically, when the density is higher, so that the typical distance between the ion and the atoms is at the order of or larger than our ion, they behave differently from what you would expect from a neutral, from just a scattering length approximation. This R ion becomes important. Whereas when the density is very low compared to R ion, it's enough to use the scattering lengths. They behave like they do in the neutral systems. And you can look at various things like the residue and so on. And this also actually behaves qualitatively. There's some qualitative difference between the residue for these charged quasiparticles in the Fermi sea as compared to the neutral counterparts. But I can see that I only have 7 minutes, and I would rather spend my time on the last part, which is our latest work, which we like very much, and Mikael is part of this. So I have spent you 7 minutes of this thing here. So here so now we discussed the properties of mobile quasiparticles in either mobile ions, either in a Fermi gas or in a BEC. What I will do now, and we found these quasiparticles. I said this is motivated by this Landau theory of quasiparticles. So, but the problem, an important ingredient of quasiparticles is how they interact. So if you write down, if you look in books on Landau theory for quasiparticles, and this is also what you want to use if you want to predict properties of many-body systems, you need to understand how these quasiparticles interact. It's like the second half of Landau theory is how they interact. And people have looked for this interaction between quasiparticles in the neutral gas community, but have not been able to. They are vigorously looking for it, Rudi Grimm and Svierlein and so on. I'm working with Grimm, and he sees faint signals of the quasiparticle interaction now. But our motivation is that since you guys in the ion community are very good at measuring spectroscopy of the phonon modes, maybe you can see this induced interaction in your experiments. And it's important, as I said, for Landau theory, because you needed to be able to describe superconductivity, collective modes, and so on. It's like the second half. If you just know the first half of Landau theory, the energies of the quasiparticles, it's not enough. You also need to know how they interact. And at a fundamental level, even elementary particles interact via an induced interaction. So the induced, I forgot to say that the interaction between quasiparticles is due to the exchange of sound modes in the surrounding medium, or density fluctuations. It's an induced interaction mediated by the surrounding medium. And all interactions at the fundamental level is an induced interaction. Superconductivity at a higher level is mediated by phonons or spin fluctuations. So induced interactions mediated by excitations in another medium happens all over in nature. So that's super important. And we think that since you're good at measuring phonon modes in your traps, maybe you can measure the interaction between two ions now in an RF trap mediated by density modulations in the surrounding medium. So let's examine how that works. So here we, just for the theories, we write down the Hamiltonian is now such that now the two ions is just a static potential. You have the surrounding medium and just have a static potential. And then if you have the separation scale, so you can use the pseudopotential, perturbation theory is just correct. For weak interactions, you can use, so if the interaction between the ion and the surrounding medium is weak and you have the short range value of the hardcore repulsion, there's a completely well-established many-body theory for how to do this. And it's perturbation theory in the scattering length, which reduces to the perturbation theory in the Fourier transform of the potential when the Born approximation is valid. And you can calculate the interaction between the two ions now, basically scales with the density correlation function of the surrounding medium. So the interaction between them is determined by how well does the surrounding medium propagate density oscillations. And then you can derive various analytical results in the perturbative regime. And you find, for instance, that it has a 1 over r to the fourth behavior for long range. And it scales inversely with the scattering length between the bosons. That just tells you, so I'm putting the ions into a BEC, that just tells you that the more compressible the BEC is, the better it is at mediating interactions. You can also get in other regimes, for short range, you can get your Yukawa interaction. Now let's make the interaction between the ion and the surrounding medium strong. This was perturbation theory. If you make it strong, you have to make approximations again. So what you, at the minimum, have to do is you have to solve the atom-ion scattering problem. So we do that. So we put in the exact vacuum scattering with the pseudopotential, of course, between the atom and the ion. We put that into our theory. And then we say, okay, if we have the atom-ion scattering properties taken into account exactly at the two-body level, we then say that the mediated interaction basically is that the atom comes from the BEC, scatters on the ion, it creates a Bogluber mode that propagates to the other atom and scatters on the other ion. This is a leading process for induced interactions. And when you put that in and you crank away and you calculate, this is of course an approximation because there can be higher order terms, but at least we put in the right two-body physics here. This is the strong physics, is a two-body scattering. That's inside the theory, and you can then calculate, you can then get an expression for the induced interaction between the two ions. And now it's in terms of the scattering matrix and not V. Again, this is very well established from many-body theories of short interactions with a short-range repulsion and some tail. This is just very analogous to what happens in other many-body theories with the same kind of potential. And then you can see that when the atom-ion scattering is resonant, so when you're close, when they are close to supporting a bound state, these scattering become very strong, and the induced interaction, as a consequence, also becomes very strong. This you can just see. This is what comes out of theory. So if you can now start doing this Feshbach physics that you've done already for the atom-ion physics, that should also generate a very strongly mediated interaction. So let's look at what happens. So here is a plot of the mediated interaction as a function of R for a given Bose-Einstein condensate density, coherence length, and so on. And if you go close to resonance, the interaction just increases. Then a bound state appears. You can't see it now. It's a bound state appears here at this value, and then the interaction is very strong, and then it goes down again. So this is the type of interaction. Let's skip the Fermi gas due to time, because you can do the same for the Fermi gas. The interaction mediated by the Fermi gas is basically down compared to the BEC because the Fermi gas is less compressible. So it will be harder to see induced interactions in the Fermi gas, much harder, because it's basically down because the Fermi gas is more compressible. It's down by the compressibility of the Fermi gas as compared to the BEC. But the fun thing is, for the Fermi gas, you see these RKKY oscillations, these Friedel oscillations, they are there. It could be fun to see as a function of distance between the ions, these loads and the induced interaction. The bottom line, so now I have 45 seconds in the end. So I said that the idea is we were motivated by the fact that Michael convinced me that you are very good at looking at collector modes or phonon modes of these ions. You can do it with high precision. So here's an in-phase mode. But the in-phase, when the two ions move in phase, there will be no effects of the induced interaction because it's basically the spring is constant. But if you can look at the out-of-phase mode, where the two ions oscillate in antiphase, the induced interaction should affect the collector mode frequency. It's not collective, you have two ions here, but the phonon. So we're looking at just 2 ions. Maybe you have these crazy crystals. This will also affect those frequencies, but that's a harder calculation. So we look at 2 ions, and it's just a classical theory. We just now say that the 2 ions have position x1 and x2. They're living inside some RF trap. It's a one-dimensional problem, so it's very tight in the 2 directions. I'll be quick. I know I have to finish now. And then they interact with Coulomb force. So they repel each other. This you know very well, and you can plug that into classical theory to get the phonon modes. The new thing is that they also have this mediated interaction, induced interaction mediated by the surrounding BEC. I'll focus on a BEC now. You have a trap frequency of the trap along the one-dimensional direction. And if this mediated interaction was not there, the antiphase mode, out of phase mode, would just be square root of 3 times this trapping frequency here. But since the induced interaction is there will be a frequency shift. So that's the idea. And since Mikael has told me that he's good at measuring these frequencies, maybe he can measure this even though it's small. And then he can measure the induced interaction. And again, you can calculate the frequency shift as a function of the trapping frequency and as a function of the scattering length or the pseudopotential. And you can get quite large shifts. In particular, if you use a tight trap. This is for tight trap over here. This is for a loose trap here. Because the mediated interaction goes as 1 over r to the 4th, whereas the Coulomb goes as 1 over r. So if you can make it tight, the tighter the better, the bigger the effect of the immediate interaction. And I'll just finish by saying that, so here all frequency shifts are above. So this should say, this says, that's annoying, but it says 10 to the 4 here. So all frequency shifts are above 10 to the 4 here. So all frequency shifts at this plot here should be observable. And this just tells you how much you have to tune the Bose, the atom ion scattering length to get observable shift. So in this side, this range, the shift is observable. This is a logarithm is above -4. And then, so this is for a specific example. And then the theory even predicts an instability that the mediated interaction should win over the Coulomb, but that's a breakdown of the theory. So we think that if you can tune the scattering length between the atom and the ion to the same extent as has been demonstrated, so here's this Feshbach paper for ions. If you can tune it at the same extent as they've done for neutral gases, there's a hope that you can see it. So I'll finish. Thank you very much.
Okay. Olivier was first, and then Tilman, and then Rowie. I think, or did...
Of different species, right?
Yes.
Because then you don't have any kind of charge mobility or whatever. Yeah, I mean, so assume that you take rubidium and rubidium plus. Then you would have some kind of charge mobility there, and so I suspect it is not included in what you say, right? You should have an ion of different species for all the things to work.
This calculation is for, do you remember the mixture for this calculation here? It's barium lithium, this one.
Yeah, but what I mean is that if you have ion and atom which are identical, then you have to revisit all the model, because then you have to include some kind of exchange between the particles, because of course the charge would just travel all around. So my point is that, would you agree with that, or would you say that no, it's valid also for rubidium, for let's say for ion and atom of the same species? That would be an interesting thing.
I think we have to discuss this, but I would say superficially that it should be the same because they're distinguishable, right? So an ion, rubidium ion, and
you just don't know where is the charge.
Okay, maybe you're right. We can discuss this, but
maybe Sadiq will say more about that in his talk. So.
Okay, but these are for 2 different.
Yeah.
Yeah.
This is what that was my question. Okay.
Yeah.
Thanks.
I had a question. First, I had the same question as Olivier, but that's already answered, I guess. But then, what about finite temperature here? I mean, your theory is 0 temperature, right? And has no finite temperature, yes. And if you take a mixture which has a heavy partner, let's say, or so, yes, and you have finite mass, then you have to probably extend your model
Yes.
So you are assuming ideally very light atoms, let's say, and extremely low temperatures. But what happens if you have a finite temperature?
Yes.
like
The answer, easy answer, which I also think is correct at this point, is of course finite temperature is interesting, but as long all these calculations for the interaction mediated by the BEC is for zero temperature BEC.
Yes.
When you heat it up, you start getting. So I would say that I would be very surprised if you get quantitative or like qualitative effects when the condensate fraction is close to 1. So if you stay below a half TC, the condensate fraction is close to 1. It should be relatively
even
accurate.
If your temperature is sort of close to the S-wave scattering limit or even higher of the atom-ion collision.
Who's speaking?
Here, I'm speaking.
Yes, then yeah, okay, so there's also yes, that's correct. So you also, if you open up different channels,
yes, is what I mean.
Yes,
Yeah,
okay, that's what you mean.
Channels
yes,
at finite temperature than just the one channel that you are looking at here, right?
Yes, we look at the S-wave channel here.
Only
yes.
at the S-wave
Yes.
channel, and therefore you have to have very cold with respect to the S-wave
yes.
limit of the atom-ion collision, which is possible, of course, for lithium and very light atoms, but much harder for rubidium or cesium or so. Yes,
yes, I would say that the framework, the theoretical framework is, so when my postdoc Xiang does the calculations, she projects onto the S-wave channel to make the numerics easier. But I guess if you open up more channels, you can do it, but it becomes more difficult. Yeah.
Okay, thank you.
So thank you very much for a very clear and great talk. I have a comment and a question. The comment is that you mentioned that mediated interactions were not measured or barely measured in neutral atoms, and both in the group of Cheng Chin in Chicago and in our group together with Nir Davidson, we measured RKKY interactions mediated between bosons through a degenerate Fermi gas.
Yeah, okay, we can, yeah, okay.
But
yeah.
Well, we can discuss it. But
yeah.
The question is, you mentioned that with the Fermi gas, the interactions are smaller due to the fact that it's less compressible.
Yes.
But when you think of interaction which is mediated between ions that are far away, the scaling of RKKY interactions, so on top of the Friedel oscillations, you have a dipolar 1/r cubed type scaling. So if the ions are far, wouldn't that be a better option as compared to bosons?
So you're talking about this is 1/r cubed, is that correct? Yeah, that's true. That could be the case, but my guess would be that it's just, if you go far away, it's probably better than the BEC because it's U-cover, or it's 1/r to the 4th for long range. But the Coulomb would completely overwhelm. It goes as 1/r. You want, if you look at the relative frequency shift. So here are your RKKY. But if you look at the relative frequency shift for BEC, you need the trap to be very tight. Here, if you look at this thing, because you want it to be stronger than the Coulomb. The Coulomb is just a strong bare interaction between the ions, and you want the mediated to be significant compared to that. So if you take them far away, I don't know. I mean, one would have to look at the numbers, but my guess would be that maybe the induced interaction between the fermions is stronger than between bosons, mediated by bosons, but the Coulomb is relatively stronger. Yes. But then I think this relative, you see the relative frequency shift, I'm plotting here the frequency shift, the frequency minus the frequency you would have if there was vacuum between the ions. And that will go, you see that goes down when you make the trap looser.
And I would like to, oh, it's which is this one.
Okay, I didn't think about that mode at all. So for me, that's a good idea. Yeah.
Yeah.
So because there the Coulomb is no. Why would that be
The
better?
trap and the Coulomb can basically no, by tuning the radial the frequency.
Because the Coulomb is still there. Hmm. No, I mean for our I mean that's a good idea we can discuss because this collective mode calculation or this phonon mode calculation is not difficult for us because it's a classical calculation. All you need this Hamiltonian here. So if you say that, yeah. So it's the hard bit to calculate is this where is it? But let me just say that the hard bit to calculate is this stuff here, the induced interaction. If you have this, the rest is classical.
Right, just very briefly. So the thing is that when you have this interaction, so let's say we stick with the lithium. Typically, lithium condensates are very small. I mean, they are like, 10 to the 4, some number into 10 to the 4 atoms or something of that sort. Now you are making a density wave in this because of the interactions. So can you kind of quantify what is the level of density variation that you are actually getting in the theory?
What do you mean, the level of this?
Because if you have like a few times 10 to the 4 atoms, I mean, there's a limit to how much compression, I mean, how much of the density fluctuation you can have, variation you can have in the.
So you have nonlinear effects. Okay, yeah. That's a good question. I would expect for 2 ions in a BEC of 10,000. I'm not. Well, I don't. Of course, this assumes that the density modulations is a perturbation for the BEC. So there's some feature there. I mean, the simple answer is if you have many bosons and just 2 ions, you would expect that it should work at least qualitatively, right?
Okay, so
Yeah.
let's do this over coffee then.
Yeah.
So